All right. So today we're going to be going through the SkeeterSat calibration. As I mentioned earlier, this is going to be your first foray into taking data and analyzing this data. There's a couple of supplies that you will need here. The most important, of course, being your assembled SkeeterSat. If you haven't already had your chance to finish up your assembly, that's all right. You can come back to this lecture later, and we'll have these lectures posted on YouTube for you to follow along. The other things that you will need: a 9-volt battery to put into your SkeeterSat, a multimeter just to make sure that you are, in case you run into any troubleshooting issues. You will also need a beaker of water, a hot plate or some other means of warming up that water, a freezer or a bag of ice, or any other way that you can cool off that water, and a thermometer. So the point of this calibration is you want to find the relationship between your frequency that is being emitted from your SkeeterSat and temperature. Now, as you can see right here, the frequency that is emitted from your SkeeterSat is not actually just one frequency. It is a number of frequencies going together at the same time. These are what are known as harmonics. There are a number of harmonic frequencies, and using the spectrogram program, which you should have installed onto a laptop with a speaker, you can actually measure this frequency and these frequencies, and from that you can actually calculate what the fundamental frequency is. Now we'll actually get into this a little bit later when Aaron's going to show a bit about how to use the spectrogram program, as well as how to calculate what is known as the fundamental frequency of the SkeeterSat. And that fundamental frequency is the actual goal of the experiment. We want to know how that fundamental frequency changes as the thermistor heats up and cools down. And so how do we go about doing that? So we have a bit of what we know what our experiment is. We want to find that relationship. So we want to make sure that the temperature of the thermistor remains consistent. So we are going to submerge it into, just like how Aaron mentioned in his lecture, a water bath, so that we can remove those fluctuations. The water bath, especially after you stir it, you will have a nice consistent temperature throughout the water. Now, you might ask, why not use just ambient air? And the problem with that is air temperature varies from spot to spot, from location to location, and it changes rather quickly. Think while you're sitting on the back porch in the middle of the summer and you have like a fan blowing on you. It's a bit cooler while you're under that fan, but the moment you step out of it, it's hot again, and you'll start sweating. It's much the same for this experiment. So we can't really use air. We could use some other methods as well, but water is easily available, and we can change the temperature of it rather easily. So what you will need, and I'm actually going to swap my shares here to my camera. Hello. So what you will need here is, what we have here is we have a beaker of water. I already was warming this up while Aaron was doing his lecture. And so what we will do, it's a bit hot, is whenever you get your SkeeterSat, we will put in our 9-volt battery, and then we will be submerging the thermistor into the water. And if you can hear it, you can actually hear the pitch of the SkeeterSat actually starting to go up because this water is hot. And we can actually see that the temperature here is around, well, gotta wait till it settles out, about 42, 43 degrees Celsius. And what's important is we're going to make these measurements at varying temperatures so that we can see what that curve is from 0°C, ice water, all the way up to potentially the boiling point of water, and we want to see what that curve is. That curve you will find is actually not completely linear. You will actually see that it will curve off at the higher temperatures because the thermistor is not a purely linear device when it comes to its response to temperature. From there, what you will need to do is the speaker is right here, and you will need to get whatever microphone you use, whether it is a one that you can plug into your computer, or if you're using your laptop microphone, you'll want to make sure that this speaker is close enough that your microphone can pick it up. And then I'm going to hand it off over to Aaron for showing a bit about how the spectrogram program works, so you can actually look at what that frequency is.
All right. So, like Josh mentioned, this is a piece of software called Spectrogram. There's a zip file on the LACES website that you can download. It's just a download and run. There's no installation. But what this software is it's something that's called a fast Fourier transform software. But basically what it does is it reads the input of sound from your microphone on your computer, and then it breaks it up into the individual frequencies that make up an individual sound. So you have two axes. So the x-axis here is an actual axis in time. So when I actually start the software, you'll see this pan from right to left or left to right as new data comes in. The y-axis is the frequency. And if you notice on the numbers here, as I move the cursor around, it tells you what time you're at and what frequency you're at. And then what the actual color or the darkness of the grayscale here is just how intense that frequency was at that time. And what you see up on top is basically just a waveform of the actual sound. So once you open this software up, you're going to have a blank screen. This just has data because I had already ran it. So what you want to do is you want to go into File, and then you want to scan input, and it's going to pop up this menu with a whole bunch of different settings. But most importantly, you want to concentrate on this scale in decibels here. So this is basically how sensitive the software is to whatever the sound is. And you're probably going to want this set to the 90 here, which is the maximum value, which is the highest sensitivity. And then the other two important settings is this, what's called this FFT size in points. And what this basically tells you is how many different frequencies there are in that y-axis. So if you look at this range here, when I make this FFT size smaller, the range actually goes up. So right now I'm going to display frequencies from 0 to about 22,000 hertz. Whereas if I turn it all the way up here, it's going to only go from 0 to 600, so 689. So in general, what works best is to start on a higher or a wider band so that you can see where the signal is going to come in. And then if you need to, you can then go back and adjust it to a more zoomed in. So again, this 512 is the most zoomed out, and this 16384, that's the most zoomed in. So I'm just going to pick, to start with, this value around 2000. And then the other setting I can adjust here is this band setting. And what I'm doing is I'm just shifting where the window is that I'm looking at. So you can see at minimum, it's from 0 to 5500. So if you were to look at this, you'll see that no matter where I put this, you know, the difference between the min and the max is always 5500. I'm just changing where in particular I'm looking. But so I'm just going to set it for the min value initially, and once you have that set, you hit OK. So you'll see I'm actually recording data here, and because I'm talking, I'm actually putting out a whole bunch of different frequencies. The human voice is made up of a whole bunch of different sounds. So if I plug in the SkeeterSat and I stop talking, you'll see that a few particular values are going to get highlighted. So if I hit stop, I'll stop recording. Now you can see that each one of these vertical bands, that is when the beep was actually happening. And within each one of these vertical slices, I've got a number of horizontal lines. And what that is what are called different harmonics of the same frequency. So when the speaker vibrates to make that sound, I not only get like it vibrating 100 times a second, I'll pick up 200, 300, 400, etc. So these are just different frequencies that are all multiples of the same frequency, which is called the fundamental frequency. And the things that are like 2 times it, 3 times it, 4 times it are called the harmonics. First harmonic, second harmonic, etc. So if I want to figure out what that fundamental frequency is, I can take the difference between 2 of these harmonics. So if I use my cursor here, I can tell, okay, this value is 2724 hertz. And then this one is 3629 hertz. So the difference between those two would be a measurement of the harmonic frequency. But you want to think about, okay, I want multiple measurements of whatever that frequency is. And as we discussed, you want it to be independent. So if I take this value and this value, well, now I don't want to use this one and this one because in both cases it depends on what this is. Additionally, you'll see on the frequency there's a plus or minus 11. So that is basically how wide each individual pixel on this picture is. So one thing you can do is if I want to get a more accurate value, so once I've figured out, okay, I need to be between 2600 and 4000, I can go back to the scan input. I can then go to a higher resolution and adjust, a higher resolution, so that a narrower window. So, and then I can adjust this to around the values I just had. So here I'm a little bit below that value of 2000, and I was a little bit above 4000. So hopefully I've got this set right. Let me plug the SkeeterSat back in and then hit OK. So you'll see here that I've got like the bottom value but not the top one. So basically I need to go in and make a adjustment. And as you can see, I still didn't get it right. So you're going to have to sort of repeatedly do this until you get a good value. Oh, sorry. So again, scan input, and I want to adjust whatever this band is up and down. And eventually you may decide, well, they're too far, they're spaced too far away, so I need to actually go back to the previous value. So again, you can see I've got this value here and this value here. So one other thing I would add is, so right now I'm just using the mic on the built-in microphone on my laptop. If you have some sort of external microphone, you can actually put that physically closer to the speaker that's making noise, and that will give you a little bit easier to see value. And I think that's pretty much it for the spectrogram software.
The only other thing that I highly recommend you guys do is, if you, Aaron, would you mind sharing the spectrogram program real quick again? For one of the things that you're going to have to do is you're going to have to write a report on this. And it's important that you capture the data that you have. And one of the things we do want to see in your reports is this screen here. So if you actually go to File there, you can actually see you can export this image, this data out as an image. Or alternatively, you can do a snapshot or a screenshot of it. Just make sure you you include that data into the SkeeterSat report. Now, I am going to actually talk a little bit more about the SkeeterSat report here, saying as that is going to be the first major document that you guys will have to put together. So I should have it right here. So the SkeeterSat report has a number of contents within it. So we want you to describe what the SkeeterSat is, what its major components are, what does it do. That's a very important aspect of this. Then we also want you to explain to us what the objectives of this calibration is. Why are we calibrating the SkeeterSat report? We're not just telling you just to do it to do it. There's an underlying reason behind it. What information do you hope to learn about? Also, you need to record what materials you were using. What items were, did you have your thermometer? Do you have a hot plate? Did you use a microwave to warm up your water, or a hot plate? It's important that you write down what materials you were using, and also how you actually made your measurements. How did you make your recording? What was your process behind it? And then finally, we want to see what your calibration results were. Ultimately, we want to see a table and a graph of these results. The table, we will want to see all your individual measurements, including your harmonics, the calculation of your fundamental frequency, and the temperatures that you measured as well. And then at the end, we want you to write a conclusion about what results you got from your calibration. Was it successful? You can have an unsuccessful calibration. Now, if that is the case, then I would highly recommend that you go and redo this calibration over again. We do like seeing good results. And also what other information that you can learn. And also, how can this information be used in the future? One of the things I also ask some students to do is they include a bit about how they might go about trying to calibrate the photoresistor as well. Now that one's a bit more tricky because we don't have a very easy way to measure the light intensity without getting some more expensive sensors. But I also like to include that as a thought experiment to include within the report at the end, within the conclusion itself.